Hi there. Thank you for joining me again to continue our discussion on algorithms. And as the topic of the day suggests, if you're looking at the screen, is that we are going to be speaking today about dynamic programming as a technique that can be used to solve problems. Now, our concern today is the generation of Fibonacci numbers. So that's what we're going to be debating about today. Now, last week, or in the previous class, we talked briefly about dynamic programming, and we used dynamic programming to talk about we used dynamic programming on what I would have called single source shortest path problems. And the problem that we looked at during that time was the Bellman-Ford algorithm. Okay, Bellman-Ford algorithm. And we said Bellman-Ford algorithm is a dynamic programming technique for solving single source shortest path problems. And we saw that it encompassed, different, different ideas that made it dynamic programming. Now, those ideas were that we could have optimal substructure property. And this optimal substructure property meant that any local solutions ended up being part of the optimal solution to the problem. So the optimal solution to the problem, optimal solution is essentially made up of the solution to some sub-problems, okay? Some local solutions. We're going to talk about that in a few minutes. So that's what we saw with Bellman-Ford. We also saw that there were overlapping sub-problems. Essentially, within that regard, particularly with Bellman-Ford, we were looking out at a path between a vertex A and a vertex B. And we said if there was a vertex C, so supposing this was A, and this was B, and this was C, essentially we could look at A to B as a sub-problem because A to C, the main or part of the problem, A to C essentially subsumes A to B as happening as well. So there are overlapping sub-problems. A to B is a sub-problem that essentially is overlapping to the sub-problems A to C and so on. So we saw that within the context of Bellman-Ford. So the conversation today is this technique, if it's a general technique, so to say, then it means it can be applied to multiple problems, okay? So not just, single source, shortest path problems and so on. So we want to use this idea in Fibonacci numbers. So that's what we are going to be able to do when we speak about that now. So let's look at one problem, which was, something that we all have seen before. This is Fibonacci numbers. We encountered Fibonacci numbers previously when we were thinking about divide and conquer. We looked at it when we were thinking about recurrence. So essentially about recurrence, that's what we are looking at before. So the first thing to notice is supposing somebody gave us, a number and they ask for us to calculate the Fibonacci numbers, then the pattern is if it's 0, if the number that we have been given. So this, let me think about this as the set of numbers or the set of naturals, the set of natural numbers, including 0. So the naturals are here, okay, including 0. So 0 is one of them, this is 1, this is 2, this is 3, this is 4, this is 5, and so on and so forth. Then with regard to the set of the naturals, the Fibonacci of some number n, which is in the set of naturals, which is in the set of naturals E, will be if the number is, if n is 0, then that number is 0. If n is 1, then that number is 1. If n is 2, then that number is 1. If n is 3, that number is 2. If n is 4, that number is 3, and so on. So if you look at these numbers quite carefully, you'll notice that if it's 0, then it remains 0. If it's 1, it's 1. And then when it's 2, essentially we are adding the previous two. 0 plus 1 is 1. 1 plus 1 is 2. So these two numbers make this 1. These two numbers make this 1. And then these two numbers make this 1, and so on. And therefore, for the Fibonacci, so the Fibonacci of the Fibonacci 2 is 1, the Fibonacci of 3 is 2, the Fibonacci of 4 is 3, the Fibonacci of 5 is 5, and so on. Remember, we are adding just the three numbers, the two numbers prior to it. So the first question is, looking at this question, well, I can see the answer there, but thinking about this question, what is the recurrence equation for this algorithm? Like, what is the recurrence equation for this algorithm, for thinking about the Fibonacci numbers as algorithms and so on? And what is the running time based on the recurrence that you have drawn? So I want you to take 2-3 minutes to think about it, speak to the next person next to you, and see what those numbers would contain. Okay, essentially, what is this question A, and what is this question B, and so on. Think about that for a minute. Now, supposing you thought about it, then other thing you'd like to think before you answer this is, comparing to what you're just thinking about now regarding what the running time is, what the currents of the algorithm is, and what the running time is. Also point about what do you observe from this tree that we have drawn here regarding the Fibonacci numbers, and then start thinking, can this problem be solved in a more efficient way? Okay, just think about that for a minute. All right, as you continue to think about it, so let's see what the solution to this was. Okay, so this part here. Okay, so let's see what this solution to this problem is. So we have Fibonacci numbers. We have already articulated what it means. So we say that we have some set of naturals, including 0. And so they have 0, 1, 2, 3, 4. And the fib of some n in the set of the naturals is 0, is 1. So this appears to be the base case here. And then from there, we're adding two numbers, this guy here. So this is our recurrence. So this is our recurrence now, and this is our base case here. Base cases, two base cases here. If it's 0, it's 0. If it's 1, it's 1. And then the recurrence equation is here. And this works for any n greater or equal to 2. So this will be 1. This will be 2. This will be 3, dot, 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 and so on and so forth. Now, let's think about the tree. We have f of n here. N could be some number like 5, for example. So if n was 5, let me take, I don't know whether we're able to get another pen. Yes, we are. So let's take a red pen here and say, supposing n was 5, supposing n is 5, then this would be 5 minus 1, which will be 4. And then, we have somewhere we can write this in a better way. Possibly not, but okay, so this 5, and this is 5 minus 1 will be 4. This will be then 5 minus 1, which is 4. And then this will be 5 minus 2. So for each n, we are, we are putting that, and so on. And then this will go down. So this will become 0. This will become 1. This is 2. So in this case, this would have been f of 2. This is f of 1. And this will be f of 0 in our case here. This will be f of 1. This will be f of 2. And then this would have gone on to become f of 1 and f of 0. And similarly, so f of 0 and f of 1 is our base cases. So this is f of 2. And this essentially is f of 3 here. This is f of 3. And essentially here, this is f of 4. Okay. And similarly, on the other side of the tree, this would have been f of 3. Essentially, if somebody asks us, what's f of 5? We have f of 4, f of 3. And then from f of 3, we have f of 2. And f of 2 would then go to f of 1. And then this about f of 0. This would have been f of 5 minus 4 is 1. And then, yeah, this and so this is 4, this is 2 and 4. And then from there, f of 1 will have known the base case. So we don't need to go any further because this gives us the base case. And we don't have these numbers here. So for f of 5, you can imagine that tree that we are drawing. And the tree has how many calls? It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 calls. So we have 15 calls just to get, we have 17 calls just to get f of 5, essentially. So these, if you computed your recurrence, it would have given you that the lower bound is 2 raised to power n over 2, which is again 2 raised to power n, and then the upper bound will be 2 of n. So essentially, both the lower bound and the upper bound is 2 raised to power n, and therefore we can conclude that this is theta 2 of n. Okay, so this is an exponential problem. Exponential. Okay. Now, if you want to see the power of exponential, you're going to do that by, by programming it and see how big it would be. Think about it for a minute, that when we have f of 5, the tree has 15 calls. What about f of 20 and so on? So the idea of exponential means that these sort of tree will expand or will grow exponentially. Okay, but what do we see here? Well, we see that all these things are the same problems, right? Let's take another pen and see that. Okay, so if we just take this pen now, you can see this is f of 2 here, and this is f of 2 here. We can see this is f of 1 here, and this is f of 1, this is f of 1. In fact, f of 2 is repeated a couple of times. We have 1, 2, 3, f of 1s. F of 3 is 1, 2. F of 4 is only once, but we have f of 3 2 times. F of 2 we have 3 times. F of 1 we have 4 times. And f of 0 we have 1, we have 2, we have 3. I think we have more f of 1s and so on. So we have so much repetition. Okay, so we have a lot of repetition. A lot of repetition of the same problem, of the same sub-problem, so to say. Okay, of the same sub-problems. So I want you to think for a minute, what could we do to solve such problem, right? What can we do to solve some problem? So because we are repeating it 2 times, right? We are repeating this many, many times. But before we go to that, okay, so we could have coded this up, and the code is available. Essentially, coding it up is quite easy, right? Let's think about it. We could say the def f of n, where f is for Fibonacci. We can say, well, if n is 0, or n is, sorry, let me go back here. Or n is something like 1, then from what we have, we can just return 1, right? We can return n, and we are done. I'm so used to see. Okay, and we are done. Okay, so this is quite straightforward. Return n. Else, we can just return the Fibonacci, just call the function again, n minus 1 plus f n minus 2. And we are done with it, actually. Very, very easy code, right? Very, very easy code. We are done with it. 2 lines. That's the power of, that's the beauty of recursion, right? You don't have to write so much amount of code and so on. And so this is all really on it. Very, very simple, very, very straightforward. But remember, this is growing exponentially. Exponential, right? And it's coming here because our T of n is T n minus 1 plus T of n minus 2, T n minus 2, and then this one addition, this guy, so plus 1 here, right? Plus 1. So this technique is exponential. And we want to think about, so this technique is exponential. And we're saying, well, this will eat up so much time. Even when we try to do an f of 5, it's essentially, we have 15 calls to 8. When we have 10, this would have grown exponentially, and so on. Now, one of the things that we notice is this, that this problem here, it contains the optimal substructure, which is the one hallmark of dynamic programming. And we say that optimal substructure is that an optimal solution to a problem or an instance will contain optimal solutions to sub-problems, or good to say that local solution or solution to sub-problems are contained within the optimal solutions and so on. Again, what we are thinking is that if we just to pick here a number, somebody asked for us what's the f of 4. F of 4 is contained in by f of 3 and f of 2. And we know f of 3 is contained by f of 2 and f of 1, right? And then for f of 2, we know we need f of 1 and f of 0 and so on. So if we were to treat each function call as a subproblem, if we were to treat each one of them as a subproblem, then those subproblems contains the solution of the optimal solution, right? So this technique, the Fibonacci numbers, have this idea of optimal substructure in it and so on. Now, we also mentioned that another hallmark of dynamic programming is that we have, small number of distinct subproblems repeated many times. Small number of distinct subproblems repeated many times. For example, if somebody says f of 4, we say there is, and some numbers. For example, f of 3 is a subproblems, f of 2 is subproblems repeated, f of 3 is a subproblems repeated by calling f of 2 and f of 1. Notice that we are repeating this. F of 2 has subproblems f of 1. This has f of 0. And this one has f of 1 and f of 0 as well, right? And f of 0 as well. So there are multiple or, solutions or, that are repeated many, many times, as we can see here. We're saying recursive because when we defined our recursion before, we said recursion is a technique where a problem or a function, rather to say function calls smaller instances or instances of the same problem. Well, this is true definitely for Fibonacci, right? Because f of 4 is calling smaller instances of itself, f3. So f of 4, it's called f3, f of 2. And we'll know when we stop, when we get f0 and we get f1, because those are our base cases and so on. So this question now, the Fibonacci, definitely falls in within this rhyme of what would constitute dynamic programming, can be solved with dynamic programming because it fits in these two hallmarks and so on. So although we never spoke about this when we talked about our Bellman-Ford algorithm, but remember Bellman-Ford, when we computed it, we were maintaining some sort of solutions for each run. We called, we reduced the edges v minus 1 times, and for each v minus 1, we kept those solutions and kept reusing them. So essentially, we maintained that solutions in a table, so to say, and then we kept refining that table as we went back and forth. Similarly, we could do the same. Now, there are two variants of dynamic programming. We used the variant number 1 when we did Bellman-Ford, and here we are going to show the case so that now you can be able to understand it even much better. So, with regard to dynamic programming, there are really two main variants. Number 1 is a bottom-up dynamic programming, which is often referred as dynamic programming. So when people say dynamic programming, they mean the idea of bottom-up, and I'm going to specify what I mean by bottom-up. And then we have memoization, which is really what somebody might think about it as top-down approach. Now, let's start thinking what we could have done with this solution here. With this, our problem that we have here. Now, one way we could have looked at this solution is that if we have f of 4, we have f of 3, f of 2, f of 2. So I'm going to mark the ones that we are repeating just for us to be able to see that. We are repeating f of 2 here, f of 2 here, 2 times. Then we are repeating f of 1 here, f of 1 here, f of 1 here. And then we are repeating the f of 0 here and here, f of 0, and this is f of 0. We are not repeating f of 4 and f of 3. So if we're thinking about it, if you created a tree of this particular kind, we could tabulate the tree, or we could expand the tree until the first time we encounter f of 1. If we encounter f of 1 the first time, we could then save the results, and reuse those results when we find f of 1 again, And then for the same thing we would have done with f of 0, we could save those results so that we don't have to repeat it again. So as the name suggests, that is memoization. Essentially, we use the recursive approach, normal recursive approach, the one like the one we have before, normal recursive approach, and then save the solution or sub-solution to solution normally in a table. Now it depends on the problem, right? The table could be just an array. So this could be an array. An array could be a matrix or a matrix, and so on. This is what we mean by a table here. So here we are using the normal recursive approach, and then save the sub-solutions normally in a table, in this case, an array or a matrix of this kind, and so on. So that's what we need to be, we will need to do. Now, with regard to the bottom-up dynamic programming, this is telling us that we need to start up the solution by what is known. For example, by, we already know the base cases. And if you look at our problem here with Fibonacci, the Fibonacci numbers look like this: 0, 1, 1, 2, 3, then 5, and so on, right? That's what they know. But these are our base cases, base case. Now, with regard to the top down that we have, we start from f of 4. For example, in memoization, we start from f of 4, went all the way down until we found f of 1 and f of 0, and then put them up in a table and so on. So think about this. Here, we could have started off by thinking this is our table. Let's imagine that we have this -1. So index 0, index 1, index 2, index 3, index 4, index 5. Remember, the indices here are corresponding to our set of naturals, right? So when somebody says f of 4, we are looking at this box, right? So we could start off by filling all of them with just like -1, right? Okay, let's see something we could have done with this one. So we could start off by thinking that the table is filled up with -1s, because a 0 is a number, it's -1. And when somebody says, what's f of 4, we come here and we say, well, it's -1, f of 4 does not exist. Well, so we ask ourselves, what's f of 4? And then we'll go to f of 3. So f of 4 is f of 3 and f of 2. So we'll go to f of 3. And we said, well, we don't know what f of 3 is. So f of 3 means we're going to go to f of 2 and f of 1. And then we realize, well, we don't know what f of 3 is. So f of 3 says go to f of 2. We go to f of 2. We don't know what f of 2 means. And then when you go to f of 2, we know we need f of 1. Okay, so we come to f of 1. This is the base case. F of 1 is 1. So now we update this here as 1. And then this also needs f of 0. F of 0 is 0. So this is 0. But again, you see, we never started off with this table. We're filling up the table coming from index 0 and x1 and so on. But we never started up with the table. We started by asking ourselves what this is. This is why I said this technique is top-down approach and so on. And then, of course, now we have f of 2. We go back to f of 3. F of 3 requires f of 2. We know what f of 2 is. F of 2 required f1 and f0. So they added together. So now we know this is f of 1. And now f of 1 here needs f of 2 and f of 1. We don't need to compute f of 1. We already know what the answer is. And therefore, this is 2. And then finally, f of 4 needs f of 3 and f of 2. We go, do we have f of 3? Yes, it's 2. Do we know f of 1? Yes, it's 1. And therefore, this number here becomes 3 because of that regard and so on. Okay, so the table is being filled bottom up, but the technique itself is from top to down. We started f of 4 and then went down. With this one, it's telling us bottom up, But this is bottom up in the approach and also filling up the table. We know the base case, and it's telling us start from the base case, fill up the techniques, and then keep going and so on. So we're going to see that in a minute. So as I mentioned before, the bottom up requires filling up the table. Here we're going to have a one-dimensional table, which is really an array. Use an array here. We're just using an array. And then we already know the base case. Just put up the base case, the items in the base case, and then if somebody asks us a number, we can be able to compute it until the number is met. So simple again, in terms of programming it, let's say Fibonacci, bottom up DP, we'll ask n, start off by saying, assigning the base case. F of 0 is 0, we know it. F of 1 is 1, we know it. And then depending on what n is, we are going to say for I equal to 2, I less than n, I plus plus, just fill up the I, the dimension table. F of 1 is I minus 1 plus I minus 2. We already know this I because we are thinking F of I, if I is 2, 2 minus 1, 2 minus 2, and so on and so forth. So again, straightforward, but this technique here, as you can see, is iterative instead of being recursive. Right? So this technique here is iterative instead of being recursive. So in normal cases, when it comes to dynamic programming, we start off by thinking about the problem we have. We think about it from a recursive point of view, and then we turn that solution to be iterative so that we can fill up the table in a bottom-up manner in this case, like what we have been seeing before. Okay. So the other technique we talked about, so this will have, without showing you, I wanted you to think about what the running time and space complexity would be. Well, we need space complexity is going to be up to n. It's an array, a dimensional array. So this would have been O of n. And the running time is also easy. The running time is just filling up the table. So we're just essentially calling this. We are not doing any recursive work. So this is also going to be O of n and so on. Okay, so that's the case. Let's think about memoization. With the case of memoization, again, I'm just going to show up the work. We said for memoization, we're going to start up by, if somebody asks us what the f of some number, say 4 is, then we are going to think about it from f of 4, and then we're going to compute f of 3, f of 2, and then from f of 3, we know we need f of 2 and f of 1. And then from f of 2, we need f of 1 and f of 0, which are our base cases. And this is f of 1 and f of 0 as well, right? Which are our base cases and so on. So when you ask this one, our technique will run like this. Again, very, very recursive in manner. Okay, very recursive in manner. Fibonacci memoization, we are given number n. Then for all I, we are going to fill up a table. We're going to fill up a table. So we start off the table as null, or we can start them as -1, as I said before. Fill up the table, index 0, index 1, index 2, index 3, index 4. This is what we are looking for. And then we can start off by everything being -1, or we could have that time with it being null. The problem with null, of course, it signifies that we're using pointers and so on, and maybe that's not what we are interested in doing. All right, so then what we are going to do, we are going to call this function called fib memoization, okay? And this fib memoization it's recursive, eh? That's why we have REC here, recursive. It will take n and the table, right? N and the table. And what are we going to do? Everything is null, so f of n is null, for example, or -1. For example, f of 4 is -1 in our case. And if n is 0, then return 0. If n is 1, return 1. These guys here is our base cases. But recall that we are not filling up the base cases. In this array, we are not filling up the base cases yet. So we'll call the memoization, essentially breaking down all these tree. So this idea here, this is recursive. So we're going to break up the tree all the way down, and then start filling up the base cases when we hit them. So we are starting from the top, f of 4. So we are starting from the top. We go all the way to the down and then start filling up the table from the down to the up, from bottom to up. So here, filling table is bottom to up because we are going to start from the base case, but technique is top down. We're starting from the root and coming all the way down. So memoization is top down. It's also dynamic programming. The running time is not any better than the DP technique that we found before, but it's also recursive in manner. In most cases, as I mentioned before, when people hear dynamic programming, what they mean is this bottom-up approach. But memoization is also a good technique, particularly where repeatability of their repeatable solution, as we can see here with Fibonacci numbers and so on. So what do I want you to do? So for the next 10 minutes, what I want you to do is to compare these three techniques. The TA is going to pass you the code. I want you to open your laptops. Then you're going to be provided with a code for all the three techniques we saw. So we saw three techniques. We saw the recursive one without memoization. Okay, the recursive one without memoization. We saw recursive with memoization, the one which is top down. And then we saw the DP, which is bottom up. And I want you to try this with f of n being 5, n being 5. So maybe let me get this guy down. So what I want you to do is to do, this is n, this is f of n. You're going to do that. And then here you want to report the time the technique took, the time the technique took. So this is just row comparisons and so on. This is the time it took in number of seconds, maybe in seconds or milliseconds and so on. Google Collaboratory would give you in seconds, or you can use your machine. So check with n is 5, report to us what f of n is, do 10, do 15, do 20, do 30, and so on, and give to us what the time is, and then go all the way and do 50. So you're going to run 1, 2, 3, 4, 5, 6. Okay, and then report the solutions and and so on. So do this with your friends, the ones you're seated with, teams of 3 or 4 is good. Try to run the code and then speak about among yourselves what you see regarding this, and then we reconvene in a minute. I hope you have had some time looking at comparing different things with regard to with regard to the DP approach, which was bottom up approach to Fibonacci, and then DP or memoization approach for the Fibonacci, and also looking at the at the recursive one. Okay, I'm hoping that you had some good time looking at those techniques and be able to see how good the DP is able to solve this problem. You may have noticed this, that from recursive, we came from a problem that was 2 to the n in terms of complexity, to a DP problem, which was O of n, right? And this one also here, O of n as well. Okay, so this power, right? For both of these techniques, essentially, we considered all solutions possible. We considered all of them possible, like what we did with Bellman-Ford. We considered all of them, and we built a case where we just picked up, the best ones as we progressed with it. So in this conversation right now, we are going to look at dynamic programming approach to another interesting problem called the knapsack problem. Now, we are specifically interested in the problem called 0-1 knapsack problem, which is the one that we are going to look at. But of course, because we want to build a situation where we understand things very, very well, we would want to see how this works with regard to the greedy approach, and then build a case for the dynamic programming approach to it. Okay, so maybe we should start off by thinking, what's the knapsack problem? So this is inspired by, maybe a thief going to a store and he has a backpack and he wants to steal as many items as possible and then go sell them to another place and wants to make as much profit as possible. Or you could also think about it from the application of these in things like logistics, right? In logistics and transportation. And here we are thinking more that we have a truck that can carry a weight of some sort of W. So we have a capacity W, or the total weight that the truck can carry. And we want to load up as many things as possible with respect, of course, with a constraint to the weight, and be able to make the profit after selling them. So what do we have? We have N items. We are given N items of positive values, from W1 to Wn. So each N items has some weight assigned to them. And also we are given some positive integer, which are the values to the weight. So this positive integer could be profits. Okay, let me rewrite this here as we have items. So items 1, item 2, item 3, item 4, blah, blah, blah. And then out of these items, we are given weights corresponding to these items. So item 1 could have some weight 1, weight 2, weight 3, and weight 4. And then for each of these, we are given some profits. So this profit 1, profit 2, profit 3, and profit 4. Those are the profits that we have been given. And what we are interested in doing, we want to carry as many items as possible. So such that we are able to maximize. So maximize, remember, greedy approaches and dynamic approaches are used in optimization problem. We want to maximize profit. We want to maximize the profit PI with respect to WI, with respect to XI meaning the items. Okay, items, let me call them here XI. So PI, want to maximize PI with respect to XI. We want to maximize this, right? So here is I here. We want to maximize this with respect to constraint, with respect to that the summation of XI, WI, these weights that we actually carry, these weights must be less or equal to this weight, the capacity. This weight, the capacity. Okay, this weight, the capacity, and so on. Now, of course, the way I've written this, it means that maybe this PI must be something else that we compute, but that's the good interpretation for it. The good interpretation is this here. Okay, maybe I shouldn't even draw like that. Allow me to get this guy out. Yeah, okay, no, that's not good. With respect to. Okay, pen doesn't seem to right. So we want to maximize, we want to maximize the profits that we get, maximize profit with respect to this. So this is a constrained problem, okay? So the knapsack problem, for instance, is a constrained optimization problem. Okay, optimization problem. So in brief, we're given a set of items N, each with some positive weight WI and some sort of positive integer, in our case that we are calling profits. And our interest is to maximize the profits, with respect to the constraint that we get, with respect to this constraint, that the sum of the weights must be less or equal to weight of the capacity. Now, there are two aspects to this. One of them is what's called the 0-1 knapsack problem. And essentially with the 0-1 knapsack problem, we cannot be able to divide the problem into fraction. We cannot be able to divide each item that will be given into smaller parts. We must carry the item. So when we say carry item 1, we must carry item 1, okay? So we are computing a subset of items that maximize the total value, the sum, or the profit, so to say, and they all fit to the knapsack, and we cannot subdivide, cannot subdivide an item. Okay, cannot subdivide the item. And the next one, the fractional knapsack problem, same as the before, but we are allowed to take fractions of items. Okay, we are allowed to take fractions of items to the problem and so on. So this is good. Let's think about that. The first thing that we must think about, this is a maximization problem. From our conversation, we have seen that we can solve maximization problem or minimization or what we call optimization problem using either a greedy technique or using dynamic programming. Okay, so the first thing we want to think about is how would this be treated by greedy approach, and how then can dynamic programming be utilized to solve these kind of problems. Okay, so that's one of them. So think about it. Take a few minutes to think about how would the greedy algorithm be used to solve this. Okay, how does the greedy approach be used to solve this? So let me remind this. Supposing we are given some items, okay, some items xi. One of them is item 1, item 2, item 3, item 4, and so on. And then we're given some weights corresponding to it. Say for item 1, the weight is 2, item 3, the weight is 3, this the weight is 4, and this the weight is 5. And then the profit here, the profit for this one maybe is 4, maybe this is it's 3, maybe this is 7, and this is maybe 20 or so. Okay, so we're interested. And supposing now we are told the weight that we can actually carry, the weight we can carry is equal to 7. So think about it. So the weight we can carry is 7, this Wi, Pi, and so on. So think about the approaches that you could actually take in order to maximize that. What do we want to maximize? We want to maximize not the weight, but the profit. We want to maximize the profit, Pi. That's what so we are summing up all the Pi. We want to maximize the profit. So what would the greedy approach do? Greedy. Maybe we can think about it that for the greedy, we want to take items. So remember when we talked about greedy, we said we must come up with a rule of the thumb. So the rule of the thumb could be items with the greatest profits. Pick items with the greatest profits. Check the constraint. Remember the constraint, right? Our constraint says all the weights that we have must be less than equal to W, right? That's what we said. So check the constraint, and if it fills the constraint, copy and paste, repeat essentially, right? Copy and paste, repeat. That's what we might want to do. But what's these items with the greatest profit? How do we know the items with the greatest profit? Now, we said there are two problems. Either we carry the item and we're not supposed to subdivide it, or be able to divide up the items, right? Or be able to divide the items. Let's think about two approaches that we could take. One of them would be these weights, and these are profits. So what we could do is we could take the ratio of the profit to the weights. Think about it like when you go to the shop. I like to do this. I'm a big fan of coffee. And so sometimes they sell coffee like 183 grams for $3. 200 grams for $3.50. So sometimes I like to think, how much am I paying per gram and so on. This is the best way to think about it when you buy these things instead of the whole, right? So going with the same adage, we could think about that. We could create a new variable now, and we're going to say, what is the profit per given weight item? Essentially, this can tell us, how much we are paying for something. So for this one, for example, 4 and 2 is 2. So 4 of 2, this is 2. This is 3 and 3. This is 1. And this is 7 of a 4. And this is about 1 point something. Let's think about it as maybe 1.9 or something like that. It's almost 2. And this is 4 actually, because this is 20 over 4, right? This is 5. So this tells us very, very well how much value something really is, right? Something, how much is. And therefore, we could use this. Then maybe, now that we know this, we want to do this. Items with the greatest profit. We want to pick the items with the greatest profit. For example, this one, item 4 here, when we look at it, each weight that we are carrying, right? Each weight we are carrying gives us 5. Now compare this. Supposing we had not picked, this was weight 5. If we were worried about the weights, picking up this item, we would have been restricted of taking this item because we are thinking that we are filling up the things very, very fast. But that would not have been the case, right? So we have to think that the idea of profit over weight essentially tells us very, very clearly which ones to take. Then once we have done this, maybe another best idea is to, sort out items, sort out items. So let's sort this out. So we could have sorted out items here, xi, and then now we have 4 here because it has highest item, then 1, then 3, and then 2. So these are items based on how these weights are, right? Pi over Wi, this is 5, this is 2, it's 1.9, and this is 1, and so on. So what are we going to do? We are just going to pick items with the greater value and then check the constraint. So for example, we'll pick 4. We pick item 4, item here, profit. So if we pick 4, it gives a profit of 20. In the case that we don't need to divide it, we can take all of it. If we take, and then weight, our weight here is 5, the one we pick. What is remaining? W minus Wi, what's remaining is 2. So we could still pick items with 2. But according to this technique, we just need to go to the next one. This is 2 here. The next second item is 1. Item 1, it has a profit of 4. Supposing we pick all of it, the weight of it is 2. So we are all set. We have 2 and we are done. So we can pick item. So our solution is take item 4 and item 1, and we get a profit of 24. We pick a profit of 24. So this is good. This is good. It appears to be working very, very well. So maybe there's no problem. Okay. So there's no problem and so on. Okay. Let's see another example. So before we go there, maybe we should formalize our understanding. Is with grid strategy, we're going to compute VI of WI, essentially ratio of profit to weight, because this essentially gives us how much our contribution looks like. Grid rate take as much as possible of the item with the highest value weight, then repeat and recast what we just said. Maybe we could also say here, we're going to sort out items based on VI, WI, or profit I of WI, because it's much easier then to tick, because then it essentially we just be picking out the item, pick the second best one, and we'll not need to search for them. Once we sort, we don't need to search for items with the highest weight and so on. Okay, so let's see this example. So with this example, remember there are 2 things again that we can do. We could think about this from 0-1 and Knapsack, where we are not supposed to divide the problem. And then we can also think about it from fractional Knapsack, where we are allowed to divide the problem and so on. Let's compare these and see what we get as some sort of value and so on. Okay, I'm going to give you about 5 minutes to do that. Compare 0-1 Knapsack and fractional Knapsack. And remember, our formulation says we start off by computing the VI of WI and so on. So in this regard, we have already computed it, value of a weight, to be able to help you to do so. So essentially, you're just sorting them out and picking up the values. Okay, so supposing that you've already done that, now you may be able to see that from the greedy fractional problem, then we would have taken item 1. So this would have been, if we sort them, they already sorted out. This is 6, 5, and 4. Greedy Knapsack will take item 1, all of item 1, because that will maximize our profit for us. And then when we take item 1, which is this one, it has a weight of 2. The total weight is 4. That would have been made with 2. And then this one has weight of 3. So we would have taken a fraction, 2/3 of that, 2/3 of 15. And essentially, we'll get this computation, 12 plus 2/3 of 15. And this would have given us 22 as the answer. Now, what about 0-1 knapsack? The 0-1 knapsack would have just taken the whole, right? So would have taken item 1 and item 3. So would have taken item 1. Item 1 is 2, and so when we take it, item 1, the weight would have been 2. We go to item 3, we see that if we pick the 1 with item 3, okay, if we pick the 1 with item 3, what would happen is that we would bridge the constraint that we have. So we can take that item, and therefore we'll go to item 3. The one has only the weight of 1, and pick it, and then we'll have 3. So we'll take item 1 and then item 3, and essentially the value would be 16 and so on. But if this problem was 0-1 knapsack, well, we could have picked item 2 and item 3, because item 1 and item 3 is actually 19, right? So with regard to the 0-1 knapsack problem, this idea is not optimal, right? The grid algorithm is not optimal for 0-1 knapsack problem. It's optimal for fractional, and it's optimal because we are able to subdivide and take some smaller parts. Our formulation works very well, and it can be able to take as much as possible. But when it comes to 0-1, essentially, it does not allow us to be able to do so. So we need a better technique in order to solve the 0-1 problem. So here we need a better approach. We need a better approach for 0-1. So 0-1 knapsack problem, because it's not optimal when done with this. Now, with that regard, now think about this. Now enters our dynamic programming, and we want now to think about it a little bit more, like our dynamic programming approach. We want to think about it in a little bit more. Why is that? Now, well, number one, with dynamic programming, we are able to compute all possible solutions. This is what we did with Bellman-Ford. All possible solutions and pick the best ones. All possible solutions and pick the best one in a certain way. Now, a technique that we used, the DP that we actually use, we call it a bottom-up approach. Bottom-up approach. And essentially, we filled up a table. We filled up a table, and then from that table that we filled up, we then sort of put up all the solutions and only pick up the best ones and so on, right? One way we show that with fractional, with the Fibonacci, we added all of them, like we took all of them, one by one. And for Bellman-Ford, we had that table that we kept, repetitively putting some values on and so on. So how did it work in the knapsack problem? So the bottom-up approach tells us to build a table. So what we're going to do is build up a table. And this table is going to be, the columns are going to represent the weights. Okay, so we're going to say we have weight until 4, and this is how I'm going to do it. I'm going to start with weight 0 to mean I've not put anything into the knapsack, and then weight 1, weight 2, weight 3, weight 4, and so on. Okay, so I'm going to do this table. All right, and then here now, so these are the column here. I'm going to put up the items that we have, right? The items that we have and the weights that are going to be to have, right? So here I'll say I've not taken an item 0, and then here I'm going to say I take item 1 and I took item 2, and I'm going to take item 3 here. Okay, item 1, item 2, and item 3 there. So these are my items. So these things are items. I can put the profit. So of course the profit here is 0. Profit for 1 is 12. Profit for 2, profit for taking 2. Remember, here we are interested in 0-1 knapsack, right? 0-1 knapsack. So I do not need to think about the value to weight per se, because I'm interested in 0-1 knapsack. So 12 here, 2 gives me the value of 15, and 3 gives me the value of 4, and so on. And the values that I have for here. So the question that I'm asking myself is, if I was to pick an item, right? If I was to pick an item, what would happen, right? So, and whether I can carry it. So you think about, like, if I don't pick up an item, the table itself, okay, maybe I can say here, table, it's going to be filled up, is going to contain different profit scenarios, that I can get, different profit scenarios that I can get. So for example, profit 0, if I take an item with weight 0, well, I don't get any particular profit, right? If I take an item with profit 0, well, with a weight 0, so here, these are weights, item, sorry, these are items. We don't have item 0, or, so essentially, if I don't take an item, this is what I mean. If I don't take an item, I'm going to get 0 profit. So, and essentially the same in this particular case. And then I'm just going to make combination. Let's consider item 1. So supposing I was to take item 1, okay, let me try to get now a new pen so that we can easily see this. Supposing I had to take item 1, what would happen if I took item 1? Well, item 1 has a weight of 2, right? Weight of 2. So item 1 has a weight of 2. So I can only carry item 1 if my backpack can take an item of weight 2. That's only when I can pick it up. So let's think about it. So I take item 1. Do I have weight of 2? Yes, I can carry an item with weight 2 because I've not filled up anything. All right, so remember, I could have started off by filling these tables -1 everywhere so that I'm able to check that, okay, I've not taken an item and so on. So at weight 1, I can carry this item with value 2, yes, so I carry item 2. What is the profit? Profit is 12, yes, okay, so I can carry this item and I get a profit of 12 by carrying the whole thing, profit of 12. Now, okay, so I can't, I'm only considering one item here. Look at this. I'm only considering one item. So the total profit, if I only carry this item, will be 12 everywhere. Here at 1, when I only have the weight of 1, I can't carry this item. So this will be 0, right? I can't carry the item number 1 when the weight is 0 because, well, there's no space for it. Enough space for it. I can carry it when I have the weight of 3. I can carry it when I have the weight of 4, and so on. And the maximum profit I get is 12. Good. Now, the next thing now is to think about the item 2. So item 2 has weight of 3, right? Item 2 is called weight of 3. Now, I can only carry this item if the space where I have 3, the weight of 3, that item has not been filled up. So can I carry it? Well, yes, I could, okay? So let's take this item. It has the weight of 3. Supposing I was to carry that item with weight of 3, I'll get a profit of 15. Okay, so I can carry this item with weight of 15 here. Can I carry this item when I have the weight of 4? Yes, I could carry this item because, well, I have this. Now, can I carry both items, the weight of 2 and weight of 1? No, I can't carry both of them because both of them would give me 5. Weight of 2 plus 3 is 5. The weight of them would be 5. And I only have weight until 4. So I'm asking myself, between the two of them then, which one should I carry? Well, I'm going to carry the one with 15 because that would maximize my profits, right? So think about this. I considered in filling this board here, I considered, should I carry this one or this one, right? If I carry these, this will give me the 15, it will give me 12, this will give me 15, so I'm going to carry them, but I can't carry both. Okay, let's see here at 2, I can't carry item because it's weight of 3, so I'm going to just say 12 and 0 here. See how I'm building this? Okay, let's go on. Supposing I was to carry item with item 3. Item 3 has a profit of 1. Okay, so item 3 has a profit of 1. All right, so item 3 has a profit of 1. So let's think about that for a minute. A profit of 1. So if I carry it, I can only carry it when I have a space for 1. Yes, I do have a space for 1. Therefore, I can carry this item, and it's going to give me a profit of 4. So now, yes, I can carry this here. It's going to give me 4. Okay, great stuff. Now I'm going to consider, what about this space now here? Okay, what about this space here? Weight of 2. Now, weight of 2, well, I can't carry it. This one has weight of 1. Yes, I can carry it, you know, when I have weight of 2 in my bag, but it's only going to give me a profit of 4, right? It's only going to give me a profit of 4. And okay, so what about, could I have carried something else? Yes, at weight of 2, I could have carried something else, would have given me the profit of 12. So between the two of them, across these two diagonals, the two of them, I should carry this one that gives me the weight of 12. Okay, so this is nice, right? So let's go on. What about when I have weight of 3? Well, if I have the weight of 3 here, I could have carried the previous item. The previous weight when I considered this was 15, but weight of 3, I could also carry here when I have the weight of 2, but this will not maximize the profit. So the only one I can actually carry that would extend this is this one. So 15, much, much better. Okay, let's consider 4 now. Well, if I consider 4, I'll get 15 when I consider 4, but now I must consider if I'm carrying 15, so the weight of 4 here. If I carry the one with weight 3, I get actually 15. This is 4. What combinations would I have carried with? Well, I could carry 3. Okay, so I'm thinking about carrying this item with any other item. Okay, so this is coming from weight of 3. I got 15. I can carry one more item, this one for weight 1 here. If I carry the weight 1 and the weight of 3, I'll get 19. So I can add these to the previous one and I'll carry 19 here. Make sense? So essentially, I'm going through and carrying out. So to get a weight of 4, I can carry, we don't have any item with weight of 4. This one has weight of, has a weight of 1 only. So the item 3 has weight of 1, which is here 4. And I can add these to the previous one that had weight of 3. And both of them gives me weight of 4, which add up with 19. This is a value that I never got with the greedy approaches and so on. Okay, now the table is filled up. Nice, the table is filled up. So what items do I carry? What items do I carry? Like, how do I know that? What items do I carry given this table? So what you do then, you go to the table, to the end of the table where you have the maximum number, or the column and so on, where you have the maximum number. Here we found 19, right? We found 19. So do we have 19 elsewhere? Well, we don't have 19 elsewhere. We don't have 19 elsewhere. This is the only 19. And this 19 therefore tells us that it was contributed by carrying this item. So we must have carried. So we have item 1, item 2, and item 3. This says that we must take this item because that's where the 19 is. And then what we're going to do, we're going to think like, well, if I carried this item, the profit that remains is 15, right? 19 minus 4, the profit value is 4. 19 minus 4 is 15. So where did we get 15? Well, 2 places. We got 15 by going here or by this side. We can take any side. All right, so we got 15 by some value on this side. So this was 15, and that's how we ended up getting this value. Or we got this by going up. This was the value at 15. Now, we must consider from 15, was 15 always here? Now, we have to check, either the previous row or the previous column. Yes, we had 15 here. Okay, Was it 15 elsewhere? No, we don't have a 15 elsewhere. So this 15 must have come because of carrying this item, the item 2. So we must have carried item 2. What's 15 minus 15 is 0, so we don't need to consider anything else. So the items we must carry is 2 and 3, which essentially gives us the total of 19. Now, what did we do here? We filled up the table, and then in order to carry which items, we made series of decisions to achieve the answer. We made series of decisions to achieve the answer that we need. Okay, so that concludes our conversation regarding this technique. Again, the values are here. You could have arranged this table differently. For example, in this one, I made the table by putting the weights on one side and this side telling me which items to carry, whether I'm going to carry item 0, item 1, item 2, or item 3. I could have done that, item 1, item 2, and item 3, and then considered those values and then tabulated the numbers and so on. Now, what is the recursive functions that I was using? This is a recursive function I was using. In order to fill up a space within the table, so the table I and weight I, so these are the weights, the columns, and this was, sorry, the weights here are the rows, and here is my I, which is the indexes that I'm following, okay? The indices I'm following. This is what I did. Again, this table has been done from the bottom, 0, 1, 2, and 3, and then going up. I could start by, thinking about from the bottom and so on. So I'm saying, look for the maximum value between a couple of things. The item I minus 1 W, or if I took the item. Don't take the item by picking up the value, the previous value, or take this particular item. So if you could just go here a little bit, for example, in this case here, we consider, supposing I took the item, this bit here, supposing I took the item. If I took the item, I'll get the value of 4. If I don't take the item, I'll get the value of 0, and so on. See, the same here. If I don't take the item, I'll get the value of 12. I'll take the item, I get the value of 0 here, and so on. So here, if I took the item, So if I took the item, I'm going to add the value of the item, value of item, and then the previous row, previous column, previous row plus previous column. Okay, previous row and previous column. So essentially, I'm looking at previous row, previous column. So previous row would have been here and previous column. So I took this value here. I took this value here, this previous row, which is 3, and then added the weight, so 15. So essentially, I added the weight diagonally to get 19, as you can be able to see from there. So previous row, I minus 1, W minus WI, previous row, previous column, to take the item that you have there. So this is essentially the general formulation for this. The general formulation, max value possible for taking a subset of items, I to I with knapsack constraint W, and then, 0 W, put the zeros everywhere, and then essentially move around here. We could start off with minus infinity for W less than 0, and then we are saying don't take the item or take the item, and so on. So we would essentially do 2 nested for loops, which would give us a runtime and space complexity of N times W. Remember, W was here, right? W was here in our case. We went these columns, and then so columns was W, like that. And then N was the number of items. For example, we had item 1, item 2, item 3. Of course, we parted in with 0, 0, 1, 2, and 3, and so on. So our runtime was filling up the table was N times W, right? Our runtime of filling up the table was ONW. This is important, by the way, because this does not mean that this is polynomial. We could think about his polynomial because he's n times w, but we are also must be worried that this w here could change, right? Could change. For example, if somebody, we had only a weight of 4, sorry, in our case, we had weight of 4, but that weight could have been 16. And then our table would have been too long, would have been 16, and so on. So that's an important thing to bear in mind. And then we, of course, traced back. This is what we did. In order to fulfill the answer, we had a trace back, and that trace back went through all the different hops and plus w in order to be able to know. Yeah, we went, for our case, we didn't go all the way to 0. We went from 19, then 15. 15 became 15 minus 15, which was 0. We tried to find out where we could have found a 0. And then we found the 0 could have been here. The previous column. So the 0 could have been here. And then from 0 could have been here. And essentially, this told us that we would not carry another item. So this would have been n plus w to trace back onto this and so on. Okay, so we're going to stop there now. Please consider going through this note again, and that will be very helpful into your understanding of these techniques. Goodbye.